Good morning, guys. Today we're going to work with matrix multiplication. Yesterday or the other day we worked with adding and subtracting matrices and multiplying a matrix by a scalar. Today we're actually going to look at multiplying two matrices together. This is probably one of the more complex processes when it comes to working with matrices. Just getting the mechanics down is a little difficult at the beginning, but be diligent, stay patient, and you'll start to see it the more you work with it. First off, to even be able to multiply matrices, because we can't multiply all matrices together. Just like with matrix addition and subtraction, I had to have them in the exact same order. In this, there's only certain matrices that can be combined. And those are the matrices where the number of columns from the first matrix is the same as the number of rows from the second matrix. Very, very important. The number of columns from the first matrix must be the same as the number of rows from the second matrix. Now I'll show you why here in a minute when we start looking at an example. The actual process for multiplication says that when we're multiplying matrices, in comma, take each row from the first matrix and combine it with each column from the second matrix. So one row is going to combine with one column, and we're going to combine that by first number with first, second with second, third with third, and so on. One row with one column, put all that together to produce a single entry for the product matrix. So we'll look at a lot of examples on putting these together, multiplying matrices together. So let's look at an example of multiplying matrices. You see here we've got two matrices. Let's first identify the order, the dimensions of the matrix, to see if we can even multiply these. So looking at my first matrix, what are the dimensions of it? How many rows do we have? 1, 2, 3 rows by 1, 2 columns. Second matrix, how many rows do we have? 1, 2 rows by 1, 2 columns. So we can see that the number of columns from the first matrix is the same as the number of rows for the second matrix. If you'll write it in this order right here, or in this format right here, if these two inside numbers match, columns from the first, rows for the second, we're allowed to multiply. What's really neat about it is the outside numbers, the number of rows from the first matrix and the number of columns from the second matrix, actually produces the size of our product matrix. So these two are going to tell me how large my product matrix is. So we should get a 3 by 2 matrix out of this whole thing. So should get 3 rows, 1 row, 2 rows, 3 rows, and 3 columns. Or 2 columns rather. 1, 2, 3 rows again. 2 columns, 3 rows. And the process we're about to go through will kind of lend why it is set up like that. What I like to do is label the address of each of these product entries, each of the entries in the product matrix, because that helps me keep things organized. Because remember what we said, to multiply, I've got to take my rows from column 1 and put them with my rows from matrix 1 and put them with my columns for matrix 2. So let's just look at what the address for each of these is. Now we have right here first row, first column. So row 1, column 1. Then we have row 2. My marker's in order. Sorry, still row 1. So let's go to label to keep everything organized. Column 2. Row 2. Column 1. Row 2. Column 2. Row 3. Column 1. Row 3. Column 2. So as you can see, all of my column 1 information should appear in the first column. All of my column 2 information will be in the second column. Same thing. Row 1 information will be first row, row 2, then row 3. So let's start putting these together. We'll start out putting row 1 from the first matrix with column 1 for the second matrix. So row 1 is combined with column 1. And we just combine the corresponding entries. So first number with first number. So I'm going to do -1 times -3, -1 times -3, plus +3 times -4. So I took my row 1, which was -1, 3, and put it with column 1, which is -3, -4. And we're just going to carry out that pattern for the rest of the matrix. Row 1, column 2. So row 1 and column 2. So -1 from row 1, +2 from column 2, 3, so +3 from row 1, times 1 from column 2. Row 2, column 1. So row 2 with column 1. So 4 from row 1, -3 from column, 4 from row 2, -3 from column 1, -2 from row 1, and -4 from column 1. Moving to row 2, column 2. So 4 and 2. -2 and 1. For row 3, putting it with column 1, 5 and -3. Plus 0 and -4. Then we do row 3, column 2. So 5 and 2. Plus 0 and 1. And when you see that we didn't have any extra numbers left over, and that's because we made sure that the number of columns from the first matrix was the same as the number of rows for the second matrix, because I'm matching up two numbers with two numbers. Two columns here need to match up with two rows here. That's why those have to be set up that way. If I had 3 rows here, a 3 by 2 and a 3 by 2, I'd have been trying to match two numbers with 3 values, and we obviously see that won't work because we don't have a third number to match with a third number. You can also see the reason we get this product is because we're using the number of rows from the first matrix, row 1, row 2, row 3, and the number of columns from the second matrix. So that's why the product ends up taking the rows and columns as it does. Pay close attention here. If you're very organized and detailed about how you label this, there's a lot of numbers there. There's a lot of places for confusion, but it's just putting together one row, one column at a time. So see here, in row 1, that's what I've got in black right here. Row 1, well, row 1 is -1 and 3. So -1 and 3, -1 and 3. Row 2, 4 and -2. 4 and -2, 4 and -2 on row 2. Row 3, 5 and 0, 5 and 0, 5 and 0. Same with your columns. Column 1 is -3, -4. So for all of column 1, -3, -4, -3, -4, -3, -4. Same with column 2. 2 and 1. 2 and 1, 2 and 1, 2 and 1. So the numbers aren't jumping over there and just magically combining over there. Their location in the original matrices is going to be the exact same location in the final product matrix. It's just how we're combining them together that we have to pay close attention to. So it's the product of the first value plus product of the second value. And if we had 3 values, product of the third values plus product of the fourth values plus product of the fifth values, and so on. However many rows and columns you happen to have. You can do any number of these because the process in that pattern is going to be the same. Well, let's finish the problem up and see what our final product is. I'll do it in black so we can see it. So we go through, we do the arithmetic. I should get 3 rows, 2 columns for my 3 by 2 matrix. 3 minus 12 is -9. -2 plus 3 is going to end up being 1. -12 plus 8 is -4. 8 minus 2 is 6. -15 and 0 is -15. 10 and 0 is 10. So assuming my arithmetic is correct again, that should be the product of those 2 matrices. Okay, let's look at this next example. We start out figuring out, can we even multiply these? So what are the dimensions of this first matrix here? 1, 2, 3 rows, 2 columns. So it is a 3 by 2 matrix. Second matrix, 1, 2, 3 rows by 1, 2, 3 columns. So if we look, do the number of columns from the first matrix correspond to the number of rows from the second matrix? The answer is no. It should be obvious right here, because these 2 numbers, the rows or columns from the first and the rows from the second, are not the same. Now we should be able to double check that if we had messed that up when we go to the multiplication process. I'm taking 2 numbers and trying to combine them with 3 numbers. So there's no way that I can actually multiply those together. I need another column out here. All right, so this one's not possible. Let's change it up a little bit. Let's make that 3, -2 right there. So last one was not possible, but if we manipulate it here, let's see what we get. Now, what are the dimensions of that first matrix? 2 rows by 3 columns. So we can see that I've got 3 numbers to match with 3 numbers. So the columns of the first matches the rows of the second. So I'm able to multiply. And we know that the product should be the number of rows from the first matrix by the number of columns from the second matrix. So we should get 2 rows, 3 columns. Let's get rid of that, give us some room to work. And start by labeling your product matrix. Label the address of each one of them. So I have on row 1, column 1, row 1, column 2, row 1, column 3. Different colored pens, pencils, markers really helps on this when you're first getting started keeping it organized. Row 2, column 1, row 2, column 2, row 2, column 3. And we just put together the corresponding rows with columns. So row 1 with column 1. 1 and -2. Plus 0 and 1. Plus 3 and -1. Let's go ahead and do row 2 with column 1. And the order I fill these in doesn't matter because I'm just grabbing the row and column I happen to need at any time. So I could, if I wanted to, do row 1 with column 3 right now and have jumped all the way down there. Or row 2 with column 3 and jumped over there. As long as you're organized, you can do them in any combination of rows and columns that you want, making sure we keep the order correct as far as rows from the first and columns from the second. So row 2 with column 1. So 2 and -2, -1 and +1, -2 with -1. So remember, we're just going to work our way across the rows and down the columns. 2, negative 2, negative 1, 1, negative 2, negative 1. Now let's move to the second column. So row 1 is going to be 1. I'm actually going to show you where we can speed this up. Row 1 is 1, 0, and 3. And it's going to be 1, 0, and 3, no matter where we're at. 1, 0, 3, 1, 0, 3, 1, 0, 3. All row 1 is going to be 1, 0, and 3. Row 2 is going to be 2, negative 1, and negative 2, no matter which column we're in. So it's still 2, negative 1, and negative 2. Same thing with my columns. This is all column 2. So 4, 0, 1. 4, 0, 1 for column 2. 4, 0, 1. Column 3, the same way. 2, 0, negative 1. 2, 0, negative 1 for the first part of column 1, or sorry, column 3, and 2, 0, negative 1 for the third part, or second part of column 3. So you'll get you'll get to where you see how it fits together the more you do of these, but row 1 is going to be only in row 1 positions. Row 2 information is only going to be in row 2 positions. Same with column 1, column 2, and column 3 information. If it's not in that specific row or column, it can't be in that row or column in the product. And then we'll just finish off the arithmetic. All right, so we have negative 2, 0, and negative 1 is negative 5. 4, 0, and 3 is 7. 2, 0, and negative 3 is negative 1. Close that off. Negative 4, negative 1, and 2 is negative 3. 8, 0, and negative 2 should be 6. And 4, 0, and 2 should also be 6. So here we have the product of those two matrices. So first we checked to make sure that we could multiply. 2 by 3, 3 by 3. The inside numbers match. Columns from the first match the rows from the second. So now we get the outside numbers, rows from the first and columns from the second, to produce our product matrix. Let's multiply a few more matrices together so we can talk about changing up the order of multiplying matrices. First, let's identify and see if we can multiply. So what are the dimensions of this first one? 1 row, 2 columns, so a 1 by 2 matrix. The second one, 2 rows, 1 column, so a 2 by 1 matrix. Inside numbers match. Number of columns from the first matches the number of rows from the second, so yes, we can multiply. The outside numbers tell us that our product should only have 1 row and 1 column. So 1 row, 1 column. So we're just going to get a simple 1 value, 1 element matrix down here. So we'll take row 1, which is 1 and negative 2, and we'll combine that with column 1, which is 2 and negative 1. Do the arithmetic on it. 2 plus 2 is 4. So there's the matrix, the 1 by 1 matrix. So there's a square matrix for us, a very simple square matrix that has 4 as the only entry. If you get this, do not write just a 4 with no matrix brackets on it. It's still a matrix. It's just a single value matrix. Maybe called a singular matrix. I'll have to look into that. So there is the product of these two. Now let's change up the order of these. Let's do the 2, negative 1 times the 1, negative 2. What do you expect to happen when we change the order that we multiply the matrices in? Do we expect to get the same product, that same singular matrix? Well, let's see. What is the value or the dimensions of this first matrix? 2 rows, 1 column. So a 2 by 1 matrix one row, two columns, a 1 by 2 matrix. So as we see, we can still multiply these two. Still, number of columns from the first matches the number of rows from the second. But instead of getting a 1 by 1 matrix, we're actually going to get a 2 by 2 matrix. So when we changed up the order, we actually did get a different matrix. Now let's go through and practice our process one more time. Row 1, row 2, row 1, row 2, column 1, column 1, column 2, column 2, and let's see what we get. Row 1 is 2 and negative 1, 2 and negative 1. Be very careful when you're doing this kind of technique where we throw all the row 1 information at one time, that you're working in rows and not columns. So row 1 is 2, negative 1, and 2, negative 1. No, it's not. See, that's what I was talking about. Be very careful when you're doing these. You know, somebody's been doing them for 20 some odd years, still gets tripped up when he gets in too big of a hurry. Row 1 has this single value in it, which is 2. Row 2 has this single value in it, which is negative 1. So pay close attention, don't get in too big of a hurry. Same with our columns. Column 1 is a 1. Column 2 is just a negative 2. So we can see we don't always have to be multiplying multiple values, because here when we have a column matrix and a row matrix, we don't have multiple values. They just have the one value in each row here and the one value in each column here. Go through and we do the arithmetic. You get 2, negative 4, negative 1, and positive 2. So what this shows us is that if we change the order that we multiply in, we get different matrices. Sometimes it's not even possible. Say I had a 2 by 3 matrix times a 3 by 1 matrix. Well, as we can see here, we can multiply, but if I flip the order, the 3 by 1 times the 2 by 3, here we can't multiply because they don't have the same number of columns and rows from first matrix to second matrix. So if we can't change the order that we multiply in, we don't have what property for multiplication? What do we call when we can change the order? It's commutative. So matrix multiplication is not commutative. It is very order specific. You will not get the same value or the same matrix when you change up the order, except in one case. What is the one case where we can change the order that we multiply in and still get the same matrix? When we're multiplying by what? The identity matrix. That's right. When we're multiplying by the identity matrix by a square matrix, you can change the order of it. The identity, and we'll look at that a little bit later on when we get into our inverse matrices. But that's the only time that you can change up the order and it actually still come out to give you the same matrix. Okay, last thing I want to talk about is properties of matrix multiplication. As we just said, the order is very important that we multiply matrices in. It's not associative or commutative. We can't flip the order around, but it is associative. So first property here says if I were to do B times E and then do A times that product, it's the same thing as if I did A times B multiplied by the final matrix, that third matrix. So associative, yes. Distributive, we can also distribute. Remember, the order is very important. So if A is first here, it's got to be first in each of those. Now the reason here is B plus E is the same thing as both B and E. So if A can multiply by the sum of these two, it can multiply by each one of those. Again, same thing here. If E can be multiplied after the sum of these, it can be multiplied after each one of those. And then a scalar, we can group a scalar with any one of them. You can do the scalar times the product or the product of the scalar and one of the others. So those are properties of matrix multiplication. Come in very handy when we start doing some solving systems using inverse as far as how the order in which we work them in. But remember, if it's first, it's got to stay first even when we distribute. If it's second, it's got to stay second, even if we are associating. We can't rearrange those orders that we're multiplying in. They've got to work in the same order. That's it for matrix multiplication, and I will see you in class tomorrow, guys.